I now call to order the Society's 2,443rd meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the globe rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. Our speaker tonight is Steve Stich, Program Manager for NASA's Commercial Crew Program. He will be speaking on the program and on returning America to human spaceflight. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 160 other recordings of PSW Science lectures. We invite you to explore these presentations, and if you like what you find, to become a PSW member, and to subscribe to the PSW channels on YouTube and Vimeo, as well as to PSWs on Twitter and Facebook. The Society is grateful for the sponsorship of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and by a donor who was asked not to be named. We are also grateful to the sponsor of this evening's meeting, PSW member Adarsh Deepak. Please join me in thanking our sponsors. Our hearty thanks to you all. Before we turn to tonight's lecture, in keeping with the Society's traditions, we will welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that the following new members have been elected to the Society. Paul Arvison, a research physicist with the AAAS, interested in physics, especially underwater acoustics, cosmology, computer science, and science education, who is known of PSW for many years and has attended meetings. Anita Guberovic, Executive Assistant to the President at the Institute for Higher Education Policy, interested in space sciences and space travel, biology and environmental sciences, who learned of PSW through Meetup. And Steve Stich, our speaker tonight, whose interests will be clear in some small part from tonight's lecture. Please join me in welcoming them all to membership. Welcome. PSW is a membership organization, and a participatory membership is central to PSW's mission of communicating and furthering science. I encourage everyone with an interest in science to become a member. It's easy to do using the PSW website. Go to the homepage, www.pswscience.org. Click on the blue Join button at the upper right-hand corner and follow the prompts. New members are welcomed. PSW Science is a 501c3 charitable education and professional organization. Dues payments and other donations are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2,442nd meeting and the 90th annual Joseph Henry Lecture by Carlo Rovelli on quantum gravity. James.
Good evening, everyone. On June 4th, 2021, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 90th Joseph Henry Lecture and 2,442nd meeting of the Society to order at 8:02 p.m. Eastern Daylight Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Carlo Rovelli, Distinguished Professor of Physics and Director of the Quantum Gravity Group at Aix-Marseille University. His lecture was titled, Quantum Gravity, Where Are We? The quantum properties of gravity are among the great remaining unknowns in science. Gravity operates on a field, like the other fields of fundamental physics, and scientists believe it behaves quantum mechanically in the appropriate regime. Yet there is no theory of gravity's quantum mechanical behavior. Aspects of the gravitational field include the geometry of space and the geometry of time. Rovelli said that applying these physical and temporal coordinates to Newtonian time demonstrates that a quantum theory of gravity is a quantum theory of space-time. In this context, scientists would expect a theory of quantum gravity to incorporate the quantum superposition of space-time, the quantum fuzziness of geometry, and the quantum discreteness of space and time just before gravity is quantized. To solve for this theory, Rovelli asks whether there is a consistent quantum theory whose classical limit is general relativity. If conventional methods were effective, Rovelli said, quantum gravity could have been solved in the 1930s. But those traditional approaches lead to intractable ultraviolet divergences. Recently, empirical results have given traction to loop quantum gravity by diminishing confidence in competing approaches. For example, scientists theorized that Lorentz invariances break at the Planck scale, but recent observations have ruled out that theory, making Lorentz violating solutions of quantum gravity empirically difficult. Rovelli next addressed supersymmetry, which is helpful to quantum gravity because the infinities of graviton loops are cancelled by the infinities of supersymmetric particles. But scientists have not been able to see supersymmetric particles where they expected to find them. The cosmological constant approach is also under empirical stress. Rovelli said the revelation that lambda is positive has made string theory difficult to reconcile. He does not take seriously the emphasis about dark energy. In sum, recent empirical results have shown that popular theories are either incomplete, in tension with empirical inputs, or disappointing about their own expectations. Rovelli said loop quantum gravity is the best current tentative theory. It does not violate Lorentz invariance, involve extra dimensions or supersymmetry, rely on an infinite distance, or require additional hypotheses aside from general relativity and quantum mechanics. Rovelli said the infinities of the naive quantization of general relativity based on a perturbation expansion around a fixed geometry are not real. They are shown to be not physical by non-perturbative calculation that proves that geometry is quantized at the Planck scale. Loop quantum gravity emerged from a surprise. In 1986, researchers determined that loop states are exact solutions to the Wheeler-DeWitt equation. That key, Rovelli said, unlocked loop quantum gravity. He said a good theory must be such that you can write the full equations on a single slide, and showed that loop quantum gravity could satisfy that standard. He then described the basic equations and the concepts of spin networks, spiroforms, the big bounce, and white holes. In spin networks, the volume of the quanta of space and the area of their surfaces have discrete eigenvalues, which have ultraviolet finiteness. The geometric variables describing a single quantum of space do not commute, a characteristic of the quantum fuzziness of the geometry. Spin networks also can be in superposition. In other words, spin networks give a complete mathematical description of a quantum physical space. Applying loop quantum gravity machinery to cosmology leads to the conclusion that at high density, there is a pressure due to quantum effect that slowed the collapse of the early universe and reversed it into a big bounce. Rovelli's current work applying loop quantum gravity to black holes suggests they can quantum tunnel and become white holes, which exude rather than trap information. He said black holes in the early universe may have ended their operation and become white holes, Planck-scale micrograms or cosmic powder, which would behave like dark matter. Rovelli concluded by stating the conceptual consequences of loop quantum gravity. He explained that in quantum gravity there is no time, no space, no infinity, no things, and no external observer. He then answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 10:10 p.m. The temperature in Washington, D.C., 28 degrees Celsius. The weather, partly cloudy. The number of concurrent viewers of the Zoom and YouTube live stream, 133, and views on the PSW Science YouTube and Vimeo channels, 1,058. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Excellent job on challenging subject matter. The minutes will be posted to the website in due course. Please send any corrections or comments to corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. A video of the lecture is available for everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website. We now turn to tonight's lecture. It's my pleasure to introduce tonight's speaker, Steve Stich. Steve is the program manager for NASA's Commercial Crew Program. He is responsible for setting and implementing the program's objectives. He sets strategic vision and provides management guidance in the areas of policy, planning, contract management, program processes, and organizational efficiencies. He also leads collaborative relationships with the program's partners, SpaceX and Boeing, and with other involved organizations such as the FAA. In more than 34 years with NASA, Steve has also served as, among others, Deputy Manager of the Commercial Crew Program, Director of the Exploration, Integration, and Science Directorate at the Johnson Space Center, and Space Shuttle Flight Director. Among other honors and awards, Steve was named Federal Engineer of the Year at NASA, awarded the Silver Snoopy, received 3 NASA Exceptional Leadership Medals, and also was awarded numerous NASA Outstanding Performance and Group Achievement Awards. Steve earned his BS in Aerospace Engineering from Texas A&M University. All questions will be fielded in the Q&A session after the lecture. The screen is the speakers.
Thank you very much, Larry, for that kind introduction. And it is my distinguished honor to be here with the PSW Science Organization tonight. And thank you so much for allowing me to become a member of this distinguished organization. I can certainly tell that the lectures are stimulating from the minutes that were just read. I'm here tonight to share a little bit about our Commercial Crew Program and what we're embarking upon in this program. And I'll talk a little bit about how we formulated it with this public-private partnerships. And I'll talk about the missions we're flying today, the vehicles we have, and sort of our vision for a human spaceflight. It's a pretty exciting time in commercial crew. Just today, we're getting ready for our next flight, which is the Boeing Orbital Flight Test 2. That'll be on July 30th. And so the launch vehicle that you saw roll out, that Atlas V, is being stacked in the vertical at the Cape Canaveral Air Force Station at Launch Complex 41. And the Starliner is in the progress of being fueled for the flight. So every day in commercial crew, it's a really exciting time. I'll start out by talking a little bit about NASA's sort of vision for exploration and how we fit into the broader NASA picture. If you look over on the left, it really is, low Earth orbit focused, where you see the International Space Station, which is our destination for our vehicles today. And then in the future, we really do envision a low Earth orbit economy where the ISS, the International Space Station, transitions to a commercial platform. And so the whole idea of NASA operating in LEO is really to begin to turn low Earth orbit over to commercial companies and to commercialize low Earth orbit. We really envision lots of different companies participating in low Earth orbit. And then that really allows NASA to focus more and more on the exploration program as we continue to do things in low Earth orbit with a more cost-effective vision. If you just think back to 1981 was the first space shuttle flight. Of course, that was instrumental in building the International Space Station, a totally government program. The ISS, obviously, a government-led program with lots of contractors, international partners. And then now what we're doing is transitioning to vehicles that are not necessarily owned by the government. If you look in the center of the screen, it sort of shows the moon as the current focus and the different areas that the NASA is embarking upon to go back to the moon with the goal of returning to the moon in the 2024 timeframe. You see the Space Launch System. This is the launch vehicle that is going to return the crews to the lunar surface at some point, and then the Orion spacecraft, which is the vehicle that's going to return our astronauts to the vicinity of the moon and eventually land on the moon via the human landing systems. It's an exciting time in exploration as well with the Space Launch System. The very first flight will be later this year in the October-November timeframe. This launch vehicle, the core stage, is at the Kennedy Space Center in the vertical assembly building being assembled. This vehicle, a little different than the commercial vehicles, it has a lot of heritage back to the space shuttle with the 5-segment solid rocket motors, and then the core stage, which really has heritage to the external tank of the space shuttle. And then the Orion vehicle, I'll talk a little bit more about Orion and how it was really instrumental in helping the development of the commercial crew vehicles. And so this environment is really trying to go back to the moon with the goal, as I said, of 2024. There is, in addition to the lunar surface missions with HLS, there is this lunar orbital platform called Gateway, and the difference between Apollo and the missions we're going to fly to the moon and the near-term Artemis program is really about reusability. The landers will be reusable, going back and forth from the Gateway to the lunar surface, and this Gateway will be in lunar orbit. It also has a commercial element to the Gateway in terms of having commercial resupply launch vehicles that will take cargo to and from lunar orbit. So you can kind of see, really commercial space for NASA started with the cargo missions to the International Space Station. That program was back in 2004. Transitioning, the next step was commercial crew, which is our program today. And then the next step really is delivering cargo to lunar orbit. This will be in a halo orbit about the moon, and the cargo will be delivered to this lunar orbital platform. And then the ultimate goal, of course, is Mars. And then, the vehicles are being designed to actually also deliver mass to the Mars surface at some point. But the moon is the path to Mars. We see there's a lot of benefit in going to the moon as we begin to learn and go back to the exploration. This is just sort of how we fit into the broader NASA vision in commercial crew. Our vision in commercial crew is really about having low Earth orbit be this robust, vibrant enterprise with many launch providers and a wide range of government and public uses. We even see that with the space station that you see in the vision today. The space station is a great international lab, and so the space station program is embarked upon having commercial companies fly up their experiments to the space station for a commercial purpose. We are there, NASA and the government is there to provide this wonderful laboratory. The things we can provide is a platform to do that research. It's a place in space that has plentiful power. It has astronauts that can tend to the various experiments. We can deliver cargo in the cargo vehicles to and from International Space Station and get data and the experiments down very easily through a really big pipe of getting data down to the ground. So a lot of the experiments are actually on the space station and operated by scientists in universities and labs all across the country through a way that they can command their experiments on the space station. And so the space station, I think there's a whole story about the space station and commercial spaceflight and how it really has been the anchor and the enabler for commercial spaceflight. One of the aspects of our program that's different is, although we are very focused on the International Space Station today with our vehicles and the way we travel back and forth and send our crews to the space station, but it really is helping us focus on the moon mission. And one of the things our program has done is really, it's a new way of doing business, and I'll talk a little more about that, but it reduces the cost of access to space. We are letting industry innovate and take advantage of their skills and deliver a service to NASA that then drives the cost down versus a more traditional NASA approach where we would levy many specifications and requirements on a contractor, and they would deliver a system to those specifications. So today, this new model is we will levy a certain number of requirements, certainly make sure the vehicles are safe to fly our crews to the space station and return them safely to Earth, but then do it in a little bit different way. Additionally, we really have two different purposes. We have a NASA purpose, and that really is today to safely transport our crews back and forth to the International Space Station. And that's what we've been doing. If you've been watching our flights, we've flown 3 crewed missions over the last 11 months, all SpaceX missions, starting with the Demo 2 flight, and then ending in April with a flight to the space station as well. But that is the NASA purpose. We really need these vehicles to take 4 crew to the International Space Station to carry powered payloads, which allows for a lot of great science that has to be chilled to very cold temperatures, and then return that science back home to the Earth to the various investigators. But the public purpose is also to support this LEO non-NASA market for commercial human transportation services. So it really is to have non-NASA missions. And we'll talk a little bit more about those later on. That's our public purpose, is to really, since we don't, in the past, NASA would contract with various vendors and own the vehicle. The vendor would deliver that vehicle back to NASA, and then we would operate that vehicle with usually our ops control teams. And then that vehicle was owned by the government. These vehicles are owned by the private sector, primarily owned by SpaceX and Boeing. And then they can take those vehicles, as long as they still can meet our mission demands, they can take those vehicles and use them for other missions to low Earth orbit. So it's this dual purpose of really forming this LEO economy and then also supporting our NASA missions, which is a significant departure from the way NASA has managed programs in the past. Our approach to this endeavor with commercial crew is really to define this end-to-end transportation solution. And so where we're different from previous NASA programs is, for example, for the space shuttle program that I supported for many years, it was a totally government-led effort, although we had contractors deliver the major components, the space shuttle orbiter, the main engines, the solid rocket boosters, and the external tank. But we had different contracts that went out for different pieces of that transportation system. Here we ask industry for an end-to-end transportation solution. So they would be responsible for the whole mission. So they needed to have a launch vehicle, the launch pad, the spacecraft that ferries the crew. They needed to have all the ground infrastructure to assemble and test the vehicle. They also needed to have the mission control operations for the launch and also on orbit. We had clearly stated safety requirements as well as we laid out the program. And I had the pleasure of leading a team back in 2010 when commercial spaceflight, human commercial spaceflight really began to take off with when the Obama administration proposed this commercial model. And so I had to sit down and think about, well, what are the safety requirements? And when we did that with the team, it's much like for spaceflight, what would you have? And the parallel would be, what would you have on a commercial aircraft? So you get on an aircraft, there's an oxygen system that comes down if you lose cabin pressure. There's emergency lighting. There's life rafts should you land in the water, flotation devices, fire extinguishers, that sort of thing. So I had to sit down and think about, well, what are the safety requirements for these vehicles, and what kind of requirements do we want? And we turned out that we just, we wanted a very robust abort system, and I'll talk a little bit more about that. All the way from the launch pad to orbit, we wanted the ability, if the launch vehicle had a problem, the spacecraft could safely return the crew to Earth. We wanted certain safety requirements for having fire on board or life raft, those sorts of things. If the atmosphere was contaminated in the spacecraft, it had to be able to purge the atmosphere from a contamination type event. Those are the sorts of things that we had to think about, put into the requirements. Also, how much redundancy and reliability we want in, how many safety systems do we want in the spacecraft? So we had to lay all that out. We then had competitive selection of the service providers, and we'll talk about that process in a little bit of how we ended up with Boeing and SpaceX. These were firm fixed price contracts, so quite different from human space flight. In the past, we've used a cost plus model where the government would pay the contractor for all the materials and all the analysis and any labor that they did. Well, these contracts were milestone based, to where the government only pays the contractor if they meet a certain milestone, which has a specified criteria. And then if they don't meet it, then the government doesn't pay that milestone, which was a dramatically different approach from what we've done in the past. And we use that for the development of the vehicles. We use that also today when we contract for a mission to the space station for our 4 crew. We used it for testing. We used it for operations. We used it for the whole thing. And so what this meant was, not only did the government have to have an investment in the vehicles and in the service, but the contractor also had to have that as well. We really wanted competition, and that's why we ended up selecting 2 providers, and that was a big theme through the whole way. What we really see is competition drives down the prices. It also drives innovation, and it drives some unique solutions that maybe NASA might not have thought of. We wanted a range of launch vehicles and spacecraft combinations. That's why we ended up selecting 2 different providers with 2 different launch vehicles and 2 different spacecraft to really have that diversity of vehicles. And the theme there was really assured access to the International Space Station. We knew as we moved into this model, we were moving away from the Soyuz vehicle, which is a wonderful vehicle that the Russian government has flown for a large number of years. It has a tremendous track record. We're moving to this new model. And so that's why we really wanted to, what we've seen in the past is, the DoD, in particular for their access to space, has had 2 different launch vehicles, the Delta and the Atlas, for example, and then now for those kinds of missions, they also use the Falcon 9 launch vehicle as well. So we really wanted to have those 2 diverse vehicles as part of our transportation system. To optimize for success, we had this strategy of starting with the right plan. And I would say one of the key successes in our program was when we had that small team in 2010 develop the initial requirements. We ended up with about 330 or so requirements, which seems very, very minimal. And I was always worried we had too few requirements. And then we also had to find the interface to the space station. So I think the 2 key things that we did that helped make us successful was we really thought about the requirements at the beginning. And some of our requirements are high level, like transport 4 crew members and 220 kilograms of cargo to the International Space Station and return them safely. That's one of those requirements. And when you decompose that, then that really decomposes into the launch vehicle, how big that launch vehicle has to be, what kind of throw weight it needs to have to the space station, how big does the spacecraft have to be. It really drove a lot of things, but we had really high level requirements. We also allowed industry to have unique and alternative approaches. And you can see that here. You can see the Boeing Starliner CST-100 vehicle, which has a service module and crew module. And then you see the SpaceX Dragon, which has a trunk and aerodynamic fins and a nose cone that protects the docking system, and a little different design. Both decided to use a push or abort system, which was new and innovative, but both had a little bit different approach to the way they did it. And we allowed that. As long as they met our requirements, it was acceptable to have two different approaches. We had a phased acquisition approach, and I'll show you what that meant. And then we really tried to partner with industry from the very beginning to educate them on our expectations, what our requirements were, what kind of things we're looking for. And we really see this as a partnership between NASA and industry versus the more traditional role where the NASA program manages the program and then sort of directs the contractor. We engaged industry the whole time during this acquisition approach strategy, and then we looked for feedback along the ways at things that we could do to improve. And so it was an evolutionary approach to get to where we're at today. So this is sort of how we did it. And it really started back in 2010 with that presidential announcement to have this, this commercial model. And so we had lots of different vendors. You can see here, SpaceX, United Launch Alliance, Paragon, Sierra Nevada Corporation, Boeing, Blue Origin, ATK. We started with this very small, modest $50 million development. We called this CC Development 1. And that was really just to start giving some seed money to industry to begin to mature their systems. We weren't at this time asking for a full end-to-end transportation system. We were just looking for each company to continue to mature their designs and their goals. And sometimes it was actually, almost subscale. Paragon was more about life support systems. Obviously, Sierra Nevada was about their Dream Chaser spacecraft. United Launch Alliance was about their development of an abort system for the Atlas V rocket to detect problems during potential launch anomaly and then communicate those to the spacecraft and allow the spacecraft to safely separate. That was something that launch vehicle needed. And then ATK was looking at a different kind of launch vehicle at the time. So this was really about seed money, and then we moved into another Space Act agreement, CC Dev 2, and then eventually toward bigger contracts, and I'll talk about these in a second, where these are really small, $50 million, $315 million spread out, then a little more focused on a transportation capability, integrated capability, about $1.67 billion, a small contract to get feedback on their requirements, and then this is the contract that we're operating today called Commercial Crew Transportation Capabilities Contract, and I'll talk more about that. So this is a little bit of how this went. CC Dev 1, we had a smattering of money giving to these different companies. At the time, Boeing and Sierra Nevada got almost $20 million each to then mature their systems. We moved, and these were what we call an unfunded Space Act agreement. So there was really no requirements per se in that Space Act agreement. So the contractors got to propose to the solicitation what they wanted to work on and what they wanted to mature. And you can see here, obviously, Blue Origin was wanting to advance their capability with their New Shepard, Dream Chaser for Sierra Nevada, and obviously, Boeing had their vehicle that they really wanted, the Starliner vehicle they wanted to advance. And so we moved into a little bit bigger CC Dev 2 a few years later, and then started to really start to seed a few of the bigger providers like Boeing and SpaceX and Sierra Nevada to mature their systems. We moved from that into this ICAP contract, which was a bigger contract where Boeing had a $460 million award, and then SpaceX almost the same amount of money, and also kept Sierra Nevada along as we went through that development. And really what we were trying to do here is have, 3 viable companies as we went down to this final selection for the transportation capabilities, to be able to down select. And so this again is seeding industry with starting to deliver their vehicles and maturing their systems. And what we found out with industry is they really needed this in carrot, the transportation capabilities contract, which was the big contract, which we awarded in 2014 to Boeing and SpaceX, $4.2 billion. This contract also guaranteed them test flights and then missions to the space station. And that was hugely important. What we found with industry is when you're looking to build a capability, they really need to see a number of flights that they could deliver services to before they will make major investments. And so this is where you really start to see industry making the major investments for the tooling to build the spacecraft, tooling for the launch vehicles, and how they're going to set up their infrastructure to operate. And so this contract was hugely important, knowing that this was coming for the contractors to move forward. The CPC certification products contract was some feedback. Again, this is a Space Act agreement. We got feedback on, we gave them feedback on their approach to meeting our requirements. So here we have requirements out for this big contract and a document called 1130, and then a document called 50808, which is the space station transportation integration requirements. I think another big key success to our program was the space station had a well-defined interface. We knew exactly what we needed to dock. We knew exactly how we were going to communicate between the vehicles once the vehicle was docked to space station. We knew how the vehicle needed to fly up to the space station. Those requirements were very well solidified. And so we gave the contractors feedback on their approaches to our requirements, the way they would implement standards for welding, crimping, wiring, printed circuit boards, everything that needs to go into building a spacecraft. We gave them feedback here to prepare them for this phase when we down selected to Boeing and SpaceX. So let's see, I've talked about this approach of giving a minimum safety requirements to guide their architecture. We had these formal documents that I talked about that we put out and allowed the contractors to give them feedback on those. We had technical standards that we needed them to meet. In other words, for a parachute system, for example, they needed to be able to sustain a failure of one of the main parachutes. One failure in that design, all the way through, whether it be a drogue parachute, which helps slow the vehicle down while it's up higher as it begins to prepare for landing, and then the mains, which are the ones that allow the vehicle to land safely, either in the water or on land. So we had these technical standards that we released to industry, and we wanted they could actually come forward and propose their own standards as well. So this was different than a typical NASA approach, where NASA would have a program would put out their standard for the way we want them to do structures, for example, and they had to meet every one of those requirements. Well, here we asked the contractors to, and we knew many of these contractors had their own standards within the company of how they do welding, how they manufacture printed circuit boards, how they do structural analysis, how they do fracture control, how they do many other things, and how they do avionics and meet all the requirements for having a robust avionics system. So we allowed those contractors to provide their standards, and we would look at those standards, compare them to the NASA standard. And in many cases, we actually allowed the contractor to use their own standard. I talked about the ISS design reference mission that we had and the technical requirements. We had released these requirements pretty early out so industry could see what we were thinking. I think this was really important. And then we got feedback through request for information, and then the certifications product contract. I think this feedback loop between what NASA was thinking and industry was thinking was maybe a little different in the past. NASA kind of went off sometimes on its own and sort of had a design in mind, and then they levied the specifications for that design. And then the contractors built and tested the systems to those standards. So this was a little bit different approach, which I think was successful. And I think the feedback loop from getting that feedback from industry was hugely important to try to see what were big drivers for cost and what were big drivers for maybe the technical specifications. We allowed innovation as well. We allowed, for example, SpaceX doesn't always use space-based avionics systems. We allowed them to look at using automotive grade electronics parts, for example. And we went through a process where we looked at those and figured out a way to certify those for human spaceflight. So we had quite a bit different approach in many areas. And I think that helped drive costs down and helped make us move quickly through the program. This is that certification product contract that I talked about early. We really promoted the delivery of interchange back and forth. We really wanted to give the contractor feedback where they weren't potentially meeting, and this had to be if you go back to where we were, the contractors are now in a Space Act agreement phase, which means there are no real requirements on that Space Act except milestones that we pay. We had to have a contract to give them this feedback. We sort of iterated with the contractors on certification relative to our NASA requirements. We looked at their cert plans. We looked at their verification and validation plans. We have a very robust hazard report system where they have to control all hazards with respect to the space station and then crew safety. We were able to give them over 10,000 comments on about 800 products that they delivered. And this was helped sort of set them up for the next phase where we could see where they were meeting a requirement and where they might fall short. This phase was hugely important. And then, we felt like our goal, one of our objectives was to use our crew, to use our NASA expertise to really help the partners in areas where maybe they may not have totally had the experience base. So we had veteran astronauts. You can see Doug Hurley, who was the commander of the Demo 2 SpaceX mission, and Bob Behnken. They actually spent a large amount of time out at SpaceX for many, many years prior to their flight, not only in a typical training capacity, but helping SpaceX design the interior of the cockpit, the display system, the control system, the seats, the suits, anything that really touched the crew. That was an area where SpaceX had done a great job with cargo, but they needed a little bit of expertise from NASA. And so we really provided that expertise, human in the loop testing as well. What's good enough in terms of displays and how you can fly the vehicle was something that we really did. We shared all of our best practices and we offered advice in a very collegial way. The same thing with Boeing. Sonny Williams and Eric Bowe spent a lot of time with Boeing developing their cockpit systems along with Chris Ferguson, who was the commander. And at one point, the Boeing commander of the first crewed flight test, we actually allowed the contractors to propose, if you think about aircraft development, the first person that flies an aircraft that's developed by one of the contractors, whether it be Boeing or Airbus, is usually a company pilot. And Boeing had that same model with having a company astronaut, Chris Ferguson, be the first commander and lead that development. You can see Bob Behnken and Mike Hopkins, Victor Glover here working with SpaceX. They also spent a lot of time out at SpaceX as well. And so we really were helping to prepare them where the contractors needed advice and help, not only from the crew, but also in technical areas from NASA. We would share that information that we had gained from 50 years of human spaceflight experience with the contractors. Huge partnership across the government. So we have a partnership with the Federal Aviation Administration, for third-party indemnification, and really the big change is the mission licensing for launch and reentry today for the SpaceX flights that were flying to the space station, Crew 1 and Crew 2. Those are licensed through the FAA, not NASA. So the test flights, NASA is responsible for public safety. We transitioned over to the FAA and we worked hand in hand with the FAA to transition from the test flights, for example, the Demo 1 test flight and the CFT test flight for Boeing over to these FAA licensed flights. The DoD, a lot of synergy with the DoD for the launch flows at the Kennedy Space Center and the Cape Canaveral Air Force Station. Also, we use the Department of Defense for crew rescue. We decided that the government would take upon the task of rescuing the crew in that day where there was an anomaly where the crew had to return home somewhere on the Earth. We would take that on with NASA. FCC and NTIA for communication, and then spectrum clearage. And then the differences on these flights, like the post-certification missions like Crew 1 and Crew 2, NASA would not be the investigation authority for an anomaly. It would be the NTSB and the FAA, because that's the jurisdiction that licensed those flights. And so, again, this is helping to move to this commercial model where we would like to see lots of people flying into space through the FAA, through non-NASA missions. The goals were really, regular and reliable transportation to the space station. And I think we're beginning to see that now with the SpaceX flights, where we are in a bit of a rhythm. You've seen us launch 2 increment missions to the space station to actually expand the number of crew members on the space station. The Soyuz, a wonderful vehicle, carries up 3 people. Now we can carry 4, which really helps to expand the amount of research that we're doing on the space station. And the real goal is to really increase the science. And so that 4th crew member means more time on the space station for science and research. And so we can get, at times on the space station, the one thing that governs how much research could be done was really crew time. And so having a 4th crew member is a huge part of that. And then, as I've talked about earlier, we're really trying to turn low Earth orbit over to these commercial companies. And then it really allows the rest of NASA to focus on developing the Orion spacecraft, space launch system, the Artemis missions, the human landing systems, and then all the surface systems. Because we started to realize within NASA, we just don't have enough people to do it all. And maybe today is when we look back 10 years ago, this was the turning point where industry could do this on their own. Now I'll spend a little bit of time talking about the vehicles and the differences between the 2 vehicles. We'll start with the Boeing Space Transportation System. Boeing chose to use the Atlas launch vehicle, and this vehicle has been flying for a long time successfully, probably up to about 70 flights. They chose for their performance needs, they needed what they call a 422 configuration of the Atlas. So 2 solid rocket motors. Obviously, it's the 2 RD-180 engines that's been on the vehicle for a while. And then this Centaur upper stage. The Centaur upper stage has been their workhorse for many missions, including many science missions over many years. One difference is for us, we use 2 RL-10 engines on the Centaur. We needed the extra performance to lift the Starliner. And so there's 2 RL-10 engines on the Centaur. And then there's a unique launch adapter for the Starliner vehicle. And you can see this little skirt that kind of extends down over the Centaur. And we had to put this skirt in place during a certain part of ascent. There was some loading and moments put on the Centaur. This is a pressure stabilized stage that's been flying for many years. So we had to extend this skirt down to push some aerodynamic loading down on the Centaur to get within the loads environments. So Boeing and ULA designed this skirt, which allows also the launch abort engines, which sit down in the skirt to fire should there be an anomaly during ascent. The rocket's about 171 feet tall, and of course, this stage is a LOX RP with the 2 RD-180 Russian engines, and then the upper stage is a LOX hydrogen upper stage that's been flying for a long time. So this is the vehicle that the Boeing chose, and they chose a partnership with United Launch Alliance. And we let them freely choose that as long as they could meet the requirements for aborts, which was to safely get the Starliner off the vehicle and safely return the crew should there be some kind of anomaly with the launch vehicle. We'll move to the Starliner spacecraft, which you can see. This is actually the Starliner that's going to fly here on July 30th. And again, we let Boeing decide exactly what design they would like to fly. They decided to leverage a lot of components from Orion. So the shape of the capsule is very similar to the Orion shape, and what that allowed Boeing to do is use the Orion database. You can see the hatch where the crew would enter and exit. There's a window in the hatch right here. This is what's called the ascent cover. This gets jettisoned during ascent between once the first stage burns out and the second stage ignites. This ascent cover is jettisoned. It protects the docking system and the rendezvous sensor system inside here. And then this is the service module. It really is the propulsion element. You can't see it, but the solar arrays are right here. There's a solar array panel that sits at the base of the vehicle, and most of the time that's pointed toward the sun as it flies to the space station, and it charges the batteries, which are inside the crew module. The umbilical that carries a lot of fluid connections between the service module and the crew module. The TPS, you can see there's a base heat shield. It's an ablative heat shield that sits right here. It's protected by the service module. And this is largely, the tiles here are basically shuttle-derived heritage around the hatch. And then this is flexible reusable insulation, which is very similar to what was flown on the space shuttle, so for thermal protection. So we analyzed all the parts of this system. Here you can also see these are dog houses. So this is where the thrusters are, which allow the vehicle to maintain attitude and also translate on orbit. There's orbital maneuvering engines and also reaction control system thrusters in there. And the service module separates during after the deorbit burn. So there's OMAC engines are used to deorbit the spacecraft. Then this service module separates, and then the crew module is what returns home. And so you can see when I'll talk about the SpaceX design, this crew module returns home and is reusable. That is the Boeing design. This service module actually re-enters the atmosphere and burns up in the ocean. And in order to not follow the ground track for the crew module, the service module actually has to do a disposal maneuver. So once the crew module and the service module separate, there's a series of burns that happen to make this retrograde burns to put this in the ocean. You can see Boeing chose to, their primary landing is to land on land using airbags, which is a new innovation for human spaceflight. This was the orbital flight test that flew in December of 2019, and that vehicle landing out at the White Sands Space Harbor, where we used to have a shuttle landing site. So they chose this land on land, use airbags. They have a pressurant system that feeds nitrogen into these airbags. They have to drop the heat shield to deploy the airbags. One, they're under the main parachutes, and then land on land. And the system can also land on water. So for aborts, if there was a launch abort, the crew can land safely with the airbag system on land. And so this was kind of a unique innovation, is the airbags. And then one other thing that Boeing did, you can barely see here, but the top, these are pedals for the docking system. We allowed the contractors to use a NASA-developed docking system called the NDS, NASA Docking System. It also is the same docking system that's being used for the Orion spacecraft. So there's heritage to Orion here, but Boeing chose to use this docking system. SpaceX chose to go their own way and develop their own docking system. The difference is this docking system can accommodate the Starliner mass and also the Orion mass, so it's a very flexible and unique docking system. And then the launch pad here, Boeing and ULA had to construct this crew access tower at Complex 41. So for years, this pad has been used for all the Atlas V flights, but we had to build a launch tower to get the crew over to the vehicle. This is a picture also from the OFT mission in 2019, and we're excited to have that vehicle headed out to the pad soon, and we'll see that vehicle at the pad here in July. So this is a little bit about the Boeing proposal for how they would embark upon their space transportation system. They also uniquely decided to to use NASA for the operation. So they contract with the flight ops directorate, and they the NASA personnel also operate this vehicle from the control center in Houston. And I'll talk about SpaceX using a bit of a different approach. So here's the vehicle that maybe people have seen quite a bit flying. Of course, this is the Falcon 9 launch vehicle that SpaceX has been flying for some time now. Compared to the Atlas, one of the things that was unique is SpaceX actually designed this for all the NASA requirements. We had to kind of go back and look at the Atlas in a little bit different light, because the Atlas was designed obviously well before NASA put out its requirements for human spaceflight. So we had to look at some things like fracture and structural loads very carefully to make sure that that vehicle met our requirements. And again, we had to add some avionics to that vehicle and some flight computers to look at pressures, temperatures, and command and abort. But SpaceX did this from the start. So this is the Falcon 9 launch vehicle. It's about almost 230 feet tall. It has 9 M1D engines. These are LOX kerosene engines as well, about 190,000 pounds of thrust each. And then the second stage has one, what's called an MVAC engine, and it also is LOX RP. You know, they use a different system for fueling. The Atlas fuels that rocket very early, like we did for the space shuttle. They get into a stable configuration on the LOX load on that first stage and second stage. SpaceX fuels this rocket very close to flight. If you've ever watched a countdown, they really start loading propellant at about 35 or 36 minutes prior to flight in this first stage and second stage. And that's just their model, is load the propellants very close to launch, don't allow for a lot of boil off on the LOX, and then launch the vehicle. And so the final load closes out very close to flight. We spent a lot of time working with SpaceX to human rate the Merlin engines and also the MVAC engines, and really thoroughly went through the design of the rocket. And then recently for the Crew 2 flight, we allowed them to fly a reused vehicle. So for the very first time for Crew 2, we flew a reused F9. The Dragon in this upper picture, this is the Dragon spacecraft. You can also see a little bit of difference in the way that the contractors have decided to integrate the vehicle on the launch pad. This is in the hangar, and you can see this is the transporter erector below the Dragon. And so SpaceX stacks the vehicle in a horizontal manner and attaches the Dragon in a horizontal manner, versus if you look at the United Launch Alliance configuration, all that stacking is done in the vertical integration facility in a vertical manner. And so we allowed the contractors to decide which way that they would decide to integrate the vehicle. We didn't specify that requirement. You can see the trunk. So there's a separation here plane between the trunk and the Dragon spacecraft. These are solar arrays on one half of the trunk. If we looked at the other side of the trunk, we would see some radiator panels to reject heat in space. And so this side gets to point to the sun, which is nice and warm and provides power to the batteries. The other side points to deep space and rejects heat. The abort systems between the two spacecraft are very similar. You know, SpaceX has what they call Super Draco engines in each of these pods. Inside here, there's 2 engines per pod, and they're all the way around the circumference of the spacecraft at 90 degrees. We have the Super Dracos to escape. If we go back to the Boeing vehicle, there's 4 launch abort engines inside this service module that then would allow the spacecraft to have enough thrust to escape a rocket that has a problem. SpaceX has these on the outside, and one difference, obviously the trunk is jettisoned in orbit and burns up later on. This spacecraft is what returns, and so SpaceX has a trunk they leave behind and return almost all the propulsion systems. The Boeing design leaves the service module off in an orbit that re-enters and then goes into the ocean. You can see the SpaceX docking system on the front, and then this is the nose cone that opens, and these are 4 what's called Ford bulkhead Draco engines that are used for propulsion to insert the vehicle into orbit. These are also used to deorbit the vehicle on the very front of the Dragon. And this is a unique design. I haven't, when I first saw this, most of the time propulsion is at the back of a spacecraft, but they have an innovative design with 4 Dracos here at the very front used to insert the vehicle into orbit. And then here is the docking system that they've designed and built. And then we actually tested this to make sure it meets all of our specifications. You can see at the bottom, this is one of the 2 Dragons. I don't know if this is actually from the last flight, the Crew 1 landing, but you can see they've chosen a water landing, and they have a recovery ship that they own, and then they go recover the vehicle. For the first time, if you watch the Crew 1 landing, we landed at night, and the SpaceX team did an incredible job getting to the vehicle and getting it on this recovery ship, which they own. It was about 30 or 40 minutes to get the crew out of the water onto the recovery ship. And once they get here, we can open the hatch and get the crew out. You can see the ablative heat shield, very similar to what Boeing and Orion uses. And then you can see this is what's called a SPAM. It's another ablative material that protects the rest of the spacecraft from re-entry heating. They have a couple of windows on the side. Boeing has a more of a forward window. We let them, again, trade that for whatever they need for piloting. So both the companies can trade that. And then here you see, this is the Launch Complex 39A, which was originally was an Apollo launch pad. Then it was a Space Shuttle launch pad. Now Boeing leases this from NASA, and they had to put a crew access arm, again, on this launch tower. It's much higher than the shuttle launch access was, and they use this same tower for the cargo missions. They promote cargo in a cargo Dragon. So they have a cargo Dragon that is very much like the Crew Dragon. The trunk's a little different. The trunk on the cargo Dragon can actually hold payloads inside of here. And in fact, if you follow the current cargo flight called CRS-22 on Space Station, it has some rollout solar arrays, a new solar array technology, which the astronauts will be installing in a sequence of EVAs. They had one EVA on the 16th. Another is planned for, Sunday on the 20th to go do those. And so SpaceX is leveraging their crew vehicle and cargo vehicle, which are very same now. From a NASA perspective, that's wonderful. What we see SpaceX doing is sometimes flying new technology on the cargo vehicle first. For example, they flew a battery upgrade, and we were able to follow that on the cargo vehicle first, and then we can move it over to the crew vehicle as well. And then, if you think about these 2 vehicles that I talked about compared to Orion, a little different mission. Orion's designed for deep space. These are designed for low Earth orbit. So Orion would need a little more propulsion. The Orion spacecraft is a little bit bigger in terms of volume. These spacecraft are designed for a very narrow mission: transport 4 crew to the International Space Station and return them. And then the vehicle serves as a lifeboat during that 6-month mission. So it's more of a camping trip, I would say, in these vehicles. They have a ability to have hygiene and food and that sort of thing. But the crew typically spends about 24 hours in the vehicle on the way to the space station, which you would see here as it comes up to dock. And then the landing is anywhere from about, depending on the trajectory, about 6 hours from undock to landing would be about the soonest for Dragon, and it could be up to 20 to 24 hours. So they don't spend a lot of time in the spacecraft, and about the same for Boeing, typically about a 24-hour rendezvous and maybe a 24-hour return. Just to show a little bit about the crews that are flying, this is the crew for the crewed flight test for Boeing. Mike Fink, Butch Wilmore, and Nicole Mann. Everybody probably knows these faces of Bob and Doug, the return to human spaceflight back in May. And then we also have many crews in training. This is the Crew 1 crew that just came back, Commander Mike Hopkins and his crew. And then you see the crew that's on station right now. And then this is the next crew in training as well. So we really ramped up in about the last year from the focus was on the one flight with Bob and Doug to now we have a flow of flights that we have to then keep the space station sustained and staffed. This is the commander for the next flight, Raja Shari, and the other mission specialist as well. And then this is the Starliner crew for the their first flight to the space station as well. And then so we have a total now one crew. This crew is here a debriefing. This crew is on orbit. This crew is training for Crew 3 in October. Kjell Lindgren, the commander for Crew 4, which will be likely in the spring timeframe, and then the Starliner flight as well. So we have multiple crews in training. So we really ramped up from a development, astronauts really helping with laying out the cockpits, to now lots of crews in training. And then, what we actually see now too is this this stimulation of the low Earth orbit economy. And so if you just think about the last year, in May of 2020, we flew the Demo 2 mission with Bob and Doug to the space station as our first crewed mission in 9 years, and a test flight, and then 2 other missions since then. So you see this low Earth orbit economy starting to develop. Axiom has a flight plan with SpaceX with private astronauts early next year, in probably the first quarter of next year. They want to fly a crew of 4 to the space station for a short mission. You see also SpaceX have the Inspiration 4 mission, which is a totally non-NASA mission that they want to fly 4 people in space. Likely here in the early fall timeframe, they'll fly that mission with 4 astronauts on a 3 or 4 day flight that totally not related to NASA, not going to the space station. You see Jeff Bezos also flying a suborbital flight, and you see that, and you see also Virgin Galactic also doing their suborbital mission. So you sort of see how this economy was stimulated by what we've done in commercial crew, and what really was part of our goal is to see these private astronaut missions, and NASA is adapting to how to have a private astronaut mission, how to have crew members come to the space station safely and do some work there, and how that works out. We've actually have deals with them on what they can use at the space station and supplies and so forth. And so it's kind of an exciting time as you see this low Earth orbit economy starting to take off. And then eventually, if you look at space.com in March of this year, we are looking at some point down the road, as space station retires toward the end of this decade, maybe a private space station, a commercial space station, where an entity would propose a business model to where they could own and manage a space station, and NASA would be an anchor tenant of that space station. Challenges going forward, right now, coordination across the agencies, who has jurisdiction and responsibility for low Earth orbit. Typically, that's been NASA. We don't have good transportation safety requirements that are non-NASA, and so we're working with the FAA to get those established. Who's responsible for on-orbit ops? Clearly, the FAA has jurisdiction for launch and landing. Who is responsible for on-orbit? Typically, that's been NASA. Liability and the regulatory framework for on-orbit is something that's a challenge as well. And this is something that we work a lot of, and I have to be careful in this presentation on what I discuss, because the contractors really would like to protect their intellectual property and their trade secrets. And so data rights is a big issue that we work all the time. What can we share from the contractors with other entities? Even back to NASA programs, sometimes something we do in the commercial crew, which might have applicability to Orion, we have to work through the intellectual property because SpaceX and Boeing want to protect that. So this strategy we laid out is really this foundation for NASA to acquire our commercial transportation services. It it was built and started in 2010. We built it with industry. We worked hand in hand with industry. We're starting to see some success with SpaceX delivery of crews to the International Space Station. I'm very confident that Boeing will get there as well as they do their orbit flight test in July and then work toward their crewed flight test next year. One way we look at things is the only way I'm successful is if our contractors are successful and the contractors see it the same way. So it's this unique partnership between NASA and SpaceX, NASA and Boeing, with the space station program as well. So, we really have embraced this model, and it's taken some learning. I think we are still learning on how to do it. We can still improve some other areas. And then, we're just very excited about the missions, and the nighttime splashdown in particular was unique and innovative, and we were still learning. At the Demo 2 landing, we had a big surprise with the number of ships in the area, and as we landed off the coast of Pensacola. For the night landing, we had a much better plan with the Coast Guard, and this was the first time we had a night splashdown in the ocean since 1968, but we were able to convince ourselves that it was safe, and the weather was just a beautiful day. So it was a really nice day. And that's all I had. I will offer to our audience questions at this time. So I'll turn it back over to you, Larry.
Okay, thanks. So I will start from mystery person. So Sierra Nevada's Dream Chaser was part of the Commercial Crew Program, and I understand that it's still being developed. Can you tell me whether that is still being funded in part by Commercial Crew, or is it totally private, or is it another NASA program?
Yeah, really good question, Larry. Sierra Nevada still has the goal of evolving the Dream Chaser to be a human-capable spacecraft that can launch humans and return them. They won a contract with the space station program called a Commercial Resupply Services 2. So they are developing that vehicle right now, and their prime focus is a cargo vehicle. And that vehicle is very important for the space station program. They have a module on the back of that vehicle that has a tremendous upmass capability for cargo, and then also it can return cargo. One of the challenges with the space station is, believe it or not, it's getting the science back down in volume. And so there's more science on the space station that investigators would like to get back to the Earth. And so Sierra Nevada right now is focused on that the space station resupply mission. We aren't funding them right now, but we have a relationship with them, and we have technical interchange meetings and continue to follow their design. Because again, one of my goals is to see Sierra Nevada someday fly people into space. It may not be with funding from Commercial Crew, but there might be a path there. So we continue to have a relationship with Sierra Nevada.
Yeah, on that one point, I think SpaceX is the only cargo. The crewed cargo is the only one that can land safely and bring things back. All the others are expendable.
Yeah, you're correct. I mean, today the cargo vehicle, the Cargo Dragon returns, and we return science as well in our crewed vehicles. We have an ability to return.
Right, on the crew vehicles.
Yeah, on the crewed vehicles.
Obviously, they don't burn up.
No.
Hopefully.
No.
I have one other question. It's kind of my question, which is ULA using, it has a Delta and the Atlas rockets, but they're about to be retired because the RD-180 has been basically outlawed since it's a Russian-built rocket engine, been outlawed by Congress, and it's supposed to be replaced by a Vulcan, so-called Vulcan rocket, which is undergoing development. It's supposed to be powered by the BE-4 from Blue Origin, actually. So what is the status of that? And what happens if ULA doesn't bring that program to fruition before they run out of RD-180s? Is there a backup plan, or is it just SpaceX?
We would have to address that. Right now, Boeing has purchased enough hardware from United Launch Alliance for a number of missions. So it's not an imminent problem for our program. They've went and bought a number of Atlases to carry them out pretty far. And what we would want to do is we want Vulcan to be successful, and then we would have to on-ramp that into our program. When if Boeing decides, hey, I'm going to move to the Vulcan as their launch system, we would then do a certification on that vehicle, and we would start once it starts flying. So we are following that Vulcan development and the mods to the pad and all those sorts of things right now. And then we would on-ramp that capability as a Delta certification of the vehicle. The ULA Atlas V is nearly certified for crewed flight now, and so we would have to on-ramp that. So again, that's really Boeing's model to decide as the Atlas phases out, they need to look toward Vulcan, and they've been working hand in hand with the United Launch Alliance. So we would anticipate Boeing will move to Vulcan, and we would go certify that.
Okay, a question from Ferris Assam. Ferris, can you, oh, I should read your question, sorry. So he says that the IRS could retire, say possibly in 2028. And what is NASA's future plan for ISS, and do SpaceX have a plan to be part of any further ISS developments? So that's one question, which maybe is not commercial crew, but.
Yeah, again, I talked a little bit about this idea of having a commercial space station. So, I would anticipate ISS retirement will get extended out toward the end of the decade. So we'll have the space station there. And then the idea is there's been a couple of solicitations already. Axiom has awarded a module in 2020 that attaches to ISS, and their business model is that could then be a foundational element for a future commercial station. So we've already begun to put out requests for information to have some entity propose a commercial space station, and then these vehicles would be able to go to that commercial space station. So that's really the approach for low Earth orbit. The first step was the vehicles, the cargo vehicles and crew, and the next step is that space station, which is a little more complicated. They are free to propose how big the space station would be, what the capability of it would be, and then NASA would evaluate different proposals, just like commercial crew. Probably start out with a number of those, and it's really not under our office. There's a commercial LEO office that is responsibility for doing this. One thing I would say too is NASA is probably in the middle of more development than ever with Orion SLS and the vehicles that we have. More development going on across the agency than any time in my career, certainly.
I think he had a related question, which is Russian officials indicated they could pull out of the ISS in 2025. Cosmos says its agreement with the international partners runs out in 2024. Russia has its own plans and has been making noises about doing something with China. And I guess the question would be, his question is, does NASA have a similar plan? But I think you kind of answered that. My question would be related to that. If Russia pulls out, how much of an effect does that have? And will that mean that you couldn't use Russian launch systems to get to the ISS, or they just be one-off agreements?
Yeah, that would probably be a better question for the space station program manager, but I would say the Russians have sort of made this public that they want to pull out. But at the same time, in July, they're flying up a new module to ISS called the MLM, Multipurpose Lab Module. So I suspect the Russians will stay, and we work with the partnership all the time at extending the space station out to 2030. The Russians, it's a really great reciprocal relationship. The U.S. part of the space station has certain things the Russians rely on, like power. We have a little bit more power on our side with the truss and the solar arrays. The Russians have propulsion for reboost and orbit maintenance, and so it's a great partnership. So, we're not really doing any planning for the Russians to pull out of the space station.
We have a question from Mike Helton, PSW member. Mike?
Yes, thank you, Steve. It was a very informative discussion. My question involves the Boeing land air system on dry land using airbags. And as you know, the Russians use airbags bringing their capsules back. I don't think we have ever used airbags to bring a manned capsule back, if I remember. But do you know if we've had any problems, or the real question is, did Boeing work with the Russians to develop and innovate the airbag strategy for bringing their capsule back?
Yeah, good question, Mike. The Russians use a little different system than Boeing, so they really don't use airbags. What the Russians do is they have a single parachute, and then very close to the ground, they fire some what they call soft landing rockets, and so they actually use propulsion devices to slow down at the very end, right before contact with the ground, and so it's a little different design. We have worked with Boeing on the airbag design, and it has redundancy in the way it's deployed. There's redundancy inside the bag itself. So there's two different ways to get the nitrogen gas into the bags. Redundancy in the separation of that heat shield, which then allows the airbags to unfold. We've tested it quite a bit in landing tests at Langley, and then there was a pad of work test in November of 2019 that tested the landing on the airbag system. The orbit flight test, also in December of 2019, used that system successfully, and we're about to test it again. So right now we have quite a bit of confidence in that airbag system. And you're right, it is unique for a land landing to actually cushion the final landing event. And we look at the accelerations on the crew and measure those. There'd be a anthropometric test dummy in the vehicle, just like there was on the orbit flight test, to measure the loads on the human. And so far it looks very promising. So.
Okay, thank you very much.
To those, the inflatables, when the craft lands and the weight of the craft comes down on the inflatables, does some of the air go out to cushion?
Absolutely.
Yeah, so it's a sort of, well, I forget what you call it, but
it's like a
just
shock
gonna
absorber.
bounce. Yeah, like a shock absorber.
Think about a shock absorber where the air, that system inflates. There's an inner and outer airbag, and then that air rushes out at the landing event to sort of cushion it. So it's a very innovative system.
Yeah, very interesting.
Yeah.
I have a question from Ann McQueen, who's a PSW member and is also our social media director. And she asks, will SpaceX's Starship be part of NASA's commercial crew program? And when can we expect orbital test missions of Starship? And what's the timeline for crewed missions aboard Starship to LEO? And
right now they are not part of the commercial crew program. They have proposed a derivative of Starship. They may propose that for other NASA programs, and we'll just have to see what they're doing. So right now we don't intend to award them a contract.
Has there been much interest?
Or
they're not quite there yet.
Yeah, well, they're not quite there yet, and they could propose for other NASA contracts as well, Starship, if they wanted to, in terms of derivatives for human landing systems, things like that. So we follow the development a little bit, but right now, we are really focused on our crewed mission.
We have a question from a YouTube viewer, Jorge Aponte, and he asks, how does NASA manage fixed price contracts if they involve a lot of technology that's experimental?
Yeah, we would be very cautious. Go ahead, Larry. I'm sorry. Is there another second part? Or?
Oh, go ahead and answer that one. And then we have another one from the same person.
Yeah, we try to look at the risk right before we start down an acquisition strategy path, and we felt like there was a lot of debate, I would say, before we embarked upon commercial crew. Should we really use a cost plus contract or a fixed price contract? The cargo vehicles were developed under fixed price contracts, and so we eventually looked at that development and the technology required and convinced ourselves that we could do it under a fixed price contract. We would look at the particular the mission or the need before we would go use a fixed price contract acquisition for technology development. That might not be the right thing to do. If there was a high risk, it's hard for industry to, if it's high risk, industry typically would not want to put their investment in that unless they saw some payoff or they thought they had the technology somehow in-house within their company. And so it's a fine line between which contract structure you use for which program or which application.
Yeah, the question that comes to mind is if the James Webb had been on a fixed price contract, would it have been finished a lot sooner and launched a lot sooner? Or would it have been just abandoned because the technical challenges were just beyond the ability of of those resources?
Yeah, the
So
James
it's a
Webb
question.
Yeah, the James Webb Telescope. Boy, it really is a technological marvel in terms of the way the sun shield unfurls, so some of the instrumentation, the backbone of the composite that was used to put the primary mirror together. And so I'm not sure NASA would have embarked upon a fixed price contract. I'm not sure it would have been successful. There was a lot of technology development, which has been the big challenge. And I am not very knowledgeable on James Webb at all. I would say I'm really focused on commercial crew.
It's a question nobody will ever answer because it was done on a cost plus. So this is a related question from Jorge. He asks, how does NASA manage prices as the only buyer where conditions may impose low profit, great risks? How can these technological developments be used for commercial purposes beyond NASA? Well, it's a compound question.
Yeah, I mean, we sort of have some market pricing on cargo pounds, what it costs per pound of cargo delivery. We kind of know what some of the seat costs have been from the Russians. So that's what we used a little bit of some of our benchmarks. We would do our own government assessment of a proposal from the contractors to see if the price is reasonable. We try to do that every time there's a big development. Is what do we think what does the government think it should cost, and is it reasonable, and what's the risk level to the government? So this is still a bit of an art, I would say, in terms of managing fixed price contracts. I've been at it between being the deputy and program manager almost for 6 years now, and I would say we continue to learn how to manage these fixed price contracts. What was the second part again, Larry? I probably.
What are the costs of sorry, I'm reading the wrong one. I think it was how do these things get used outside of NASA?
Yeah, I think you have to then figure out, is there a market? We've gotten a little bit better at market surveys, and you can see, at least for our vehicles with these private astronaut missions and SpaceX's Inspiration 4 mission, there is a market for people that want to pay to go into space, into low Earth orbit. And so you have to assess that market, and is there a market for that type of service? You're starting to see that a little bit with the moon, with the commercial lunar landing program, where there's a commercial landers proposed for, not for crew, but for cargo landing for science on the moon. And so we're starting to see different companies have different business models. And I think what it does is sometimes it's hard to know what some company might develop. I always use the internet as an example. And when I was young in my career, the internet was in labs at universities and NASA, and it was largely used to exchange files and data between different entities. And then, today we're doing this Zoom call on the internet. We could have multiple people, hundreds of people engaged, and I'm looking around at my desk and I've got an iPad that uses the internet, a phone on the internet. So I think sometimes, what's the imagination of business models in the future? Even things like spacesuits, there could be a commercial market for a spacesuit. If there's a commercial space station, there might be the need for a spacesuit, and then so we're starting to look at those kind of markets, and I think we're learning as we go along. That's one of the things we try to do, is always be retrospective and look at what we're doing and how could they be used in future markets.
I think we'll go to another person with a voice question, but first to follow up and make sure that I translated his question correctly. I think part of his correction, Jorge's question is probably how do you transfer the technology to make it useful beyond NASA missions? And I know NASA has a very active tech transfer function, but it's not always easy.
No, it's not easy. And then in these cases, it's even harder where if under these contracts, if it's proprietary to SpaceX or Boeing, we really cannot transfer it. That is one thing that has been a challenge. I'll talk about things we've learned a little bit and maybe to answer the question. So one thing we learned with parachutes is these large ring cell canopy parachutes used by both Boeing and SpaceX. We learned that sometimes when they deploy, that deployment is not symmetrical early on. And so the load on one line may be more than the load on another line. And a lot of the literature from Apollo said always assume they're within about 10% all the way around the canopy. Well, we learned through some testing that it was not that. And so that was a new development. How do we then share some of that data with others because it was developed on a commercial crew, either under some SpaceX testing or Boeing testing? How do we share that with the parachute community? That's one example where we're working through that right now, because we would love to share what we've learned with everybody in that community. And so we're working through those challenges. When it's a government program and the government owns the intellectual property, it's much easier to share. And that is one challenge, I would say, with these fixed price developments where we don't own the technology.
As an IP lawyer, I'd love to see those contracts and see what the clauses are about who owns inventions made pursuant to the funding. But that's a subject for another day.
Yes,
you can. A question from Frederica Durema, who is formerly the head of Air Force Research Laboratory. Frederica?
Yes, thank you for a very nice, comprehensive and very informative presentation. You talked about the successor of ISS will be for commercial developments. So I know you cannot talk about specific companies, but can you talk about areas, sectors of people are lining up to, in a sense, have commercial ventures, and what is the kind of the scope? It will be kind of experimental, exploratory development, or the range of all of those. What can you tell us about that?
Yeah, I wish I could. Thanks for the question. I wish I could answer that. We don't really know yet. We haven't gotten far enough along, and then once we get some responses back, that would be procurement sensitive right now. So, but if you are with the Air Force Research Lab, we could put you in contact with people later on that might be able to share some data with you if you were interested in participating in the commercial space stations.
Thank you.
We have a question from Al Ehrlich, another long-standing member of PSW. Al?
Yes.
He's now at the Naval Research Lab, sort of emeritus.
Yep. It's another question about pricing. I just don't understand how it works. I saw some, and early on in your talk, you had a slide with successive steps of various companies taking the same successive step that looked like, to me anyway. And there were 5 or 6 of them. And finally, at the end, the only companies involved were Boeing and SpaceX. And that looked like the most costly step. And I noticed during the whole sequence, those 2 companies had similar costs associated with their steps, but Boeing was always higher. And I wondered, are those the numbers estimated by the company, or did you and your group lay out parameters for what things should cost at each stage, or how did that pricing work?
Yeah, we early on they would propose under those space. So the difference between a SpaceX agreement and a contract is SpaceX agreement. A company proposes milestones, and NASA pays if they meet that milestone. And really, there's no requirements. The FAR contracts at the very right-hand side of that slide were really a commercial contract under the FAR. And so they proposed their prices. Each of the two contractors proposed the development cost and a series of milestones for the development of the vehicles, including, SpaceX proposed a Demo 1 uncrewed test and an in-flight abort test, and also the Demo 2 crewed flight and associated milestones. And then they proposed a cost for each of the post-certification missions, which they're flying now. And Boeing did the same thing, proposed an uncrewed flight test and crewed flight test. And then the values were a little different, and we decided to select because we really wanted this two things. We wanted the competition between the two providers, and because it was a new model, selecting two was a reasonable thing, since fixed price development for human spaceflight was way outside of what we were used to. And then, we also like having that diverse transportation system. We really have three things that made us decide to go with two different contractors. One with a bit of a lower price, and one with a little higher price to ensure we had access to space. And I think we learned that lesson just looking back on a time frame when, there was a time frame when many of the launch vehicles were down in the U.S. for various anomalies, and so we didn't really want that for crew transportation. So
Was the deliverable at the end roughly equivalent between the two companies?
The deliverable in terms of the service, they do meet our requirements. So the cargo delivery, the crew delivery, they meet all the requirements for both providers. And so there's just a little different cost between the two, and it was up to NASA. Do you keep two or do you keep one? We decided to go with two, and I think it's paid off. There's a bit of cost control when there's two, and it may seem strange because neither one would really feel like they have kind of a lock on the market, if that makes sense. So there's
Sure.
somewhat of a cost control for him.
Okay, thank you very much. I didn't understand the system.
Yeah, no, and it's tough. And again, this model is new, and we're, every day I learn something new about how to manage a fixed price contract. SpaceX and Boeing.
It's probably fair to say there's also a certain amount of congressional impetus having two, because I think there was a contingent in Congress that, they're anti-SpaceX to begin with. And then there was pro-ULA, and then there was a feeling that you couldn't just rely on SpaceX for this. It's too important. And I think you're seeing it again with the moon program. So the human moon lander, NASA didn't have the funds to award a contract to the two contenders. So they only awarded it to SpaceX. And I think Congress pulled it back in and said, you got to have two. So I think there's a little bit of congressional interest in having multiple parties for this, which is good. They're serious about getting us back into space.
And if one of the two were to fail, in our case,
exactly,
I think both Boeing and SpaceX will be successful. But with a new model where the government's not continuing to invest money for schedule delays, if there's a schedule delay, that the beauty of this fixed price contract is it doesn't, the government doesn't necessarily incur more costs. So it was a bit of a, could we really do it for crew? I think it was a bit of an experiment. And so to me, having two was smart. And if you look at, if you even go back to the Apollo development, that there wasn't two command modules, but as they were building a lot of the systems for the command module, NASA would have two different designs to scrub carbon dioxide, because they were trying to go fast. So two different vendors would propose two different systems, and NASA would down select. I think in some ways we went back a little bit to that Apollo model. It just did it at the bigger level, at the space transportation system level, versus a fuel cell or component by component.
That brings me to a question which I'm going to sneak in here before I get to Ravi Deepak's question. And that is, what's the cost per, let's say, per astronaut trip to the ISS and back on SpaceX
Boy,
90 million, 60 million, 50 million?
yeah, I would not, unfortunately, I would not have that number at the tip of my
Okay.
tongue, so.
Because my impression is that the cost of getting a kilogram to and from the space station in the SpaceX system is a lot less than it used to be. And the cost of getting an astronaut up there and back is a lot less than it was to pay the Russians to do it.
Yeah, I couldn't comment on the seat prices, but what I could say is the value of that SpaceX flight compared to what we have been doing and will continue to do with Soyuz is 4 crew, and the Soyuz has limited return capability for science. Great spacecraft, does a wonderful job returning the crew. Our vehicle can return much more cargo, and really a powered, there's 2 different versions of a refrigerator system that keeps the science samples conditioned all the way to landing, and there's a polar and a glacier, and both the Dragon and Starliner can return those. So it really is about, the value is not just the seat price, the value is that cargo and the time critical nature of getting the cargo back, and then getting that cargo, the human research. One of the things we're doing on science is really trying to understand the human body as we embark upon the longer missions to Mars. Getting that human research back in a timely fashion, getting that data to the researchers is critical. And so, that's the difference between the vehicle we've been flying on, the Soyuz, and our vehicles.
I also think in this case, there's an ROI point to be made that on the long term, the reduced cost of doing things because of the advanced systems that SpaceX and presumably Boeing have developed will make it less expensive per unit of whatever you're doing. And so it will eventually end up being less than relying on the old systems. But
and the Dragons are reusable. I mean, we've embarked upon reuse on Crew 2. That spacecraft is the spacecraft we flew on Demo 2. We'll continue to reuse Dragons, and then the Starliner is reusable as well. That crew module is reusable. So it's a different model that over time I think will pay back versus each Soyuz is a one-time use spacecraft.
So last question comes from PSW member Ravi Deepak, and it's Ardash Deepak who is sponsoring this lecture. That's his dad. He says, thanks, great presentation and overview. It's an exciting time for commercial crew. Is Tom Cruise still planning to shoot a movie on the ISS for Mission Impossible? And for the future astronauts out there, any words of wisdom or career path recommendations?
Boy, I wish I knew whether Tom Cruise was shooting a movie or not. Unfortunately, I don't have the bandwidth to keep up with Tom Cruise. But for future astronauts out there, I would say that the dream is alive, and with the right amount of hard work and pursuit of a technical field in aeronautics or engineering, and then typically astronauts have some pilot background and some high risk kind of background. We see people that were submariners or test pilots. I mean, that path is out there, and I think you're going to start to see people with different backgrounds. One of the things we see on the space station is sometimes you don't need the shuttle commander type test pilot because the vehicles are very automated these days and you're not landing on a runway. So what you really need is those skills to do science and skills to maintain space station. One of the best skills on space station is somebody that can work on stuff, and if something doesn't go quite right, can adapt. And so, I think that dream is out there for many, and NASA continues to select new and bright astronauts, and it's always exciting to see the new young faces. And I think there's a bright future for lots of astronauts, not only NASA, but private space missions as well.
Hey, Ravi, I think they should go to UCSD because right now UCSD grad is up there on the space station. That's my alma mater.
Okay. Which one, Larry?
Oh, you got me. Can't think of her name offhand.
Oh, Megan?
Yeah,
McCarthy?
Megan. Yeah.
Okay. Megan's
Yeah.
wonderful. Yeah.
A Scripps Institute oceanography grad, I believe.
Okay.
Part of
Okay.
UCSD.
Okay. She's wonderful. So as is Shane and Tama and Aki as well.
They're all pretty amazing.
Yes, they are.
So with that, I think it's a great note to end on. And let me thank you so much for spending the time with us and delivering this lecture. And I'm going to apologize, as I said I would, that we can't have you in person right now, but we're looking forward to seeing you in person when you're in DC in the future and we're allowed to meet together, hopefully for a PSW reception and dinner and lecture. But if not, for some other event, if you'll just let us know when you're in town, we'll love to have you.
Okay. Yeah, I would love to come visit. I'm looking forward to the non-COVID timeframe when we can all get together. And I wish I could have been there in person. I think that would have been a little bit better evening, but this was phenomenal. So thank you. Thank you very much for inviting me.
Thank you. Appreciate it. So maybe we'll see you in a little bit.
Okay.
And thank you everyone for joining us. The recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. Please share the links with your friends and subscribe to YouTube and Vimeo channels for notifications on new postings, and to PSW on Twitter and Facebook for news and updates on the Society's activities. And join, please join. It's easy to do using the join button on the PSW Science website homepage. Before you go, we have a few important announcements. This lecture ends the 2021 lecture series. The speakers for the fall lecture series will be posted to the website in due course. We are looking forward to a very exciting and interesting lecture series featuring more speakers on very large telescopes, quantum physics, space systems and exploration, vaccine development, and many other topics of interest. We're also looking forward to meeting again in person beginning this fall. Of course, this will depend on the Cosmos Club rules at the time and on the rules set down by the District of Columbia. But we really hope we'll be back together in person for all of the fall and beyond. But even if we can't meet in person, as soon as we hope, PSW will continue to hold meetings and lectures by Zoom, stream them to YouTube, and post edited recordings to Vimeo and YouTube. So we hope to stay in contact with you and see you again in the fall. Thank you all for joining us. And with that, last but not least, let's thank tonight's crew, James and Robin. Thank you so much for producing tonight's event. I will now adjourn the 2443rd meeting of the Society to everybody's own social hour. I wish everyone a great morning, evening, afternoon, or whatever is appropriate where you may be in the world. To all our friends around the world, the meeting is adjourned.